Testing, testing. Hello, hello, hello. Hopefully you guys can hear me. It seems like the video capture device is borked. Let me see. It's one of these OG RealSenses that I'm using. Alright, there we go, guys. As you can see, I've kind of upgraded my mouse and keyboard setup, trying a different setup here. See how that looks. I'm also bringing the microphone closer to my mouth, see if the quality is better. Alright, so today we're going to be going over a Omni3D, a large benchmark and model for 3D object detection in the wild. This is a paper coming out of Meta AI. Came out a little bit earlier this year, but they released the code under here, under their Facebook research, GitHub organization, and into the repo Omni3D. The link will be below. This is really the work of two people here, Garrick Brazil and Gikeo Shari. Okay, so these people don't. This person might actually be like a meta curator. There's a lot of different Facebook research articles or repos there. So they use the word, they use the term kind of 3D object detection. I would say that this is more scene understanding. If you look at all these data sets here, right, you have kind of the inside of a house, you have a street, and you're going to have a bunch of different objects in here, such as couches and tables and chairs, and each of those are going to fall into a bunch of categories of similar-ish objects. There's also almost like a SLAM kind of component to this as well, right, where you see that as these objects are added to this scene, they are repositioned relative to each other. Once you have more knowledge, this is kind of a variant of the SLAM problem. Yeah, I would call this more scene understanding and SLAM. 3D object detection is like those type of papers to me is when you have a single object sitting in a blank space and you're kind of walking around that single object. So Detectron 2, probably for the actual pre-trained convolutional neural network that they're using as the kind of base part of their model. PyTorch, and then Coco. We'll see what they're using that for. This is a RCNN, so probably a variant of Mask RCNN. Mask RCNN is also originally a Facebook research paper, I'm pretty sure. But it's older, you know, it's not a VIT, it's not a transformer, so, you know, it's not super hype, but they do have kind of the best scores here. They say it beats the state of the art on their new benchmark. So that's a little bit of the code and maybe looking at what they're doing with that. How about right now let's jump right into the paper here. So recognizing scenes and objects from a single image. Okay. So maybe not SLAM, right? SLAM, simultaneous localization and mapping, is not going to be a single image. It's going to be a bunch of different data, right? A bunch of different frames, usually from a camera as it moves through a scene. So maybe they are focused kind of on the single image here. 2D recognition, large data sets. Okay, so they say that basically there really isn't any good 3D data sets. Introducing a large benchmark. Okay. Omni3D repurposes and combines existing data sets, resulting in 234K images annotated with more than 3 million instances in 97 categories. Okay. So keyword here is they're repurposes and combines. So they're going to take existing 3D recognition data sets and annotate them. So you end up having kind of 250,000 images with 3 million instances total. Instances is kind of, for example, this bounding box on this car here. So 3 million, or 234,000 divided by 3 million. 234,000 divided by 3 million, or actually the other way around would have been better. It's about 12. So you have roughly 12 objects per image. And those are split into 97 categories. 3D detection at such a large scale is challenging due to variations in camera intrinsics. Yeah, so this is huge. This is something that you run into all the time when you're actually doing real-world computer vision, is that you have to be very careful about what datasets you train on and how similar the cameras and the datasets that you use are to the camera that you're going to use in your final application. So these large benchmark datasets, especially if they're repurposing and combining a bunch of existing datasets, you're going to have a large variety of cameras, which might actually help make this a more general dataset. Then they collect this dataset, and then they also, kind of as part of the paper, they throw a little freebie there. They throw a model, CubeRCNN, train it on this giant ass dataset, and then outperforms prior works. Improve single dataset performance, learning on smaller datasets. Yeah. So they basically just want to make this the new Coco. So Coco is originally from Microsoft, I believe, and for years now, Coco has kind of been the default benchmark and really one of the most useful pre-training data sets for kind of your real-world AI applications. And maybe this here, Omni3D, is Meta's attempt to kind of usurp Coco and try to maybe become the go-to open source benchmark and data set for pre-training detection models. Cool. Let's get into it. Actually, let's look at this figure more deeply here. So, Kitty is a autonomous vehicle dataset. Sun RGBD, I think that's the inside of rooms. ARKit scenes, again, also rooms. Other datasets here, Objectron, new scenes, HyperSim. It's just showing you how big each of them are. So, right, Omni3D is the combination of all of these, and it shows you just kind of how much larger it is there. So that's kind of the left side of this figure. The right side of this figure is their CubeRCNN model trained on unseen images, so basically a test. Or actually, no, it seems like here they're saying they're directly from Coco, and they're kind of significantly outperforming here. GU, PNet, and Total 3D, although these kind of sound like trash. Trash models to compare to, right? It's like they're not really pushing the state of the art here. Long-standing problem. AR, VR, again, yeah, Meta, famously kind of the metaverse company now, very interested in scene understanding and 3D object detection and kind of localization, pose detection in a home environment, right? So that Sun RGBD dataset is huge. They probably use it a lot internally. Okay, 2D object recognition. Yeah, so they want to get a 3D location and 3D extent in the image in the form of a tightly oriented bounding box. So yeah, 2D object detection, for example, in Coco, really what you're predicting is kind of a box in image space. So image space just means you have an image such as this image here, and you can say the lower corner is x equals 0, y equals 0, then it has some height, and then it has some width. So really you're just predicting basically 4 numbers. The anchor, right, the kind of position of the one of these corners of the box, and then how wide and tall the box is in image space. So really you're just predicting maybe 4 numbers. But in 3D object detection, or 3D, there's a lot more stuff, right? Not only do you have to predict the X, Y, Z position not in image space anymore, but in real space, right? Actual 3D space, world coordinates relative to the camera. But there's now also the X, Y, and Z height, depth, width of the box in actual space. So you have more numbers to calculate, and then you also have the additional complexity that you're calculating these in the actual global 3D or global coordinates, right? Relative to the camera, of course, but like in actual real world units, not in image space. Okay, urban domains, indoor scenes. Yep. Urban and indoor scenes share little insights. That's true. You don't get a ton of benefit pre-training one or the other, or training on both of them. So I think joining together these two more separate data set and benchmark worlds, I think it's a good idea, right? So you have something like Sun RGBD, and then the Kitty data set, right? Object3D is curated from publicly released datasets: Sun RGBD, ARKit Scenes, HyperSim, Objectron, Kitty, and new scenes. This is their fast, batched, and exact algorithm for intersecting over union for 3D boxes. So this actually seems pretty big, right? So like IOU, intersection over union, computer vision, is basically how much your 2 boxes overlap in image space. So right when you're doing this 2D image detection, you'll have your model will predict maybe this red box, and then you have a labeled ground truth box, which is this green one, and then to measure how good that prediction is, you use this kind of metric IOU, right? How much do these boxes intersect versus how big are the boxes to begin with? And you have to basically, in order to evaluate, in order to eventually feed gradients back to a model, you have to calculate that IOU. And calculating that IOU for 3D is going to be even more complicated. And as part of this paper, the authors say that they've found a way to make it batched such that it's significantly faster, 2 orders of magnitude faster than previous solutions. This actually kind of seems like the sleeper improvement in this paper. Okay. We design a general and simple single data set, AP performance, and urban. We'll have to see what it's actually improving from. A lot of times when researchers write these papers, sometimes they don't get the best results, and they'll purposefully pick comparison points that are a little bit easy. I'm drinking some Chemex drip coffee with MCT oil in it. Get that body in ketosis. Okay. Inspired. Cube, CNN, and their 3D properties. Okay. I'm starting to get more information about the exact numbers that they're doing here. Rotation and depth end-to-end from a single image of any domain for many object categories. So again, there's also a classification head on top of this that's predicting categories. Yep, diverse data. Right, you have a ton of different cameras because you're combining all these different data sets, so you can have all kinds of different focal lengths. And I kind of come from a synthetic data background, so to me, domain randomization is a benefit, right? Having more different cameras in your data set is probably going to make the data set, it's going to make it generalize better, right? Strong generalization. This isn't good though. They basically rectify all these images to use the same intrinsic, so they're like warping these images. That's cheating, guys. Okay. Related work. Okay, in this work, we propose a new benchmark for general 3D object detection, unified approach, 2D object detection, right? You have the kind of two-stage approaches. This is kind of the OG. In this work, we propose a new benchmark for MassGar CNN, for example, kind of old stuff where you have one network that gives you the bounding box, and then you can predict the class. So the classification head is only fed the bounding box image, and then there's all kinds of fancy tricks like NMS, right? Non-maximum suppression. Where you take a bunch of predictions and then you kind of so your model that gets these bounding boxes, it's going to predict a bunch of bounding boxes that are all kind of overlapping the same object, and kind of NMS is a hard-coded kind of heuristic-based algorithm that allows you to filter those down. So there's all these kinds of multi-staged, like kind of like hybrid approaches that use deep learning, but they're also kind of doing these tricks that have been designed by humans. Then there's what's known as kind of single-stage detectors. These are things like YOLO that kind of do the whole thing in as much of one go as you can, right? So they get rid of kind of these multi-stage, having a reason proposal network, and then you run you take that and feed into a different network and so on. So YOLO. And the reason people will do that is not just for simplification, but also if you want to run 2D detectors at a high frame rate or as high as a frame rate as you can, then simplifying the inference and making it as end-to-end as possible is a way to improve the speed. Predict 3D cuboids from single input images. Yep, there's a ton of autonomous vehicle stuff. Okay, you have kind of 3D anchors, LiDARs, right, you can augment training by using synthetically generated views. Virtual depth aims at addressing varying focal lengths. Okay, we'll see what that means. With a vocabulary of 5 or more object categories than prior works. Okay, so what does that mean? So I mean that just means here, right, where they said they have 97 categories total. So previous works probably had less categories, right? Maybe you had car, street sign, construction cone, maybe 10, right? 97 divided by 5. I would say actually probably the reason they got this is because Sun RGBD and Kitty, right? These indoor scene understanding data sets, and then the autonomous vehicle data sets are going to have different categories. So you're basically combining both of those. But I would say that you probably don't have, you're not going to have any instances of chair in Kitty, right? And you're not going to have any instances of car in Sun RGBD. So I think that distribution is not. It's not quite what they're suggesting here, where you have five times more object categories in every single image, right? I think there's still kind of a separation there in that distribution. Okay, so XY plane top and then XY, XZ plane bottom. So this is just kind of showing you how each data set relative object size is different, right? These data sets are meant for different things. They're of different things. So realistically, you're going to have a different distribution in each data set. So for example, Sun RGBD, the indoor scene data set, in this image here, which is the XY plane, right, which is the plane of the camera. There's stuff all over. There's stuff at the top of the XY plane. There's stuff at the bottom. For something like Kitty, right, which is all from the point of view of a car, it's all kind of ahead of you, right? There's nothing in this little cutout of the road in front of you, right? Like if you look at autonomous vehicle training data, right? All of it looks like this, right? It's like you kind of have this vanishing point in the distance where you're driving towards, and everything is kind of, right, everything is big in the lower right and the lower left, and kind of as it moves up towards the top of the image, it gets smaller, and then you barely have anything above the kind of center line of the image because of the horizon, which is what you see here. Coco is based on images that human took, so when humans take pictures with cameras, there's actually a bias. They will tend to center the camera on what you're looking at. So that's the bias you see in Coco, Elviz. You see some of it in Omni3D as well. This bottom image here, right, the normalized depth, That's kind of showing you the top-down view, so you can see in Kitty, right, because it's a car data set, the kind of center of the car, or like what's directly in front of the car, there's almost never anything directly in front of the car, and then you have stuff on the side, right, like the pedestrian, sidewalks, trees, and so on. Sun RGBD indoor data set, there really isn't ever anything that's super far away, right? Everything is really, really close, and that's what they're showing you here. Everything is really close to the camera. And Coco and Elvis do not have depth in such a way that you can calculate the XZ plane. Relative object size. Okay, so Omni3D in, Omni3D out. So percent of instances. I guess what this is telling you is that the out data set kind of has more variance, or it kind of, right, there's more objects that are small, and then it kind of very quickly drops down, versus Omni3D in, all the objects are kind of more similar in size. And then category, so you have, right, the 97 categories that they advertise, but you kind of have this relationship here where really the top 10 categories are accounting for the majority of the instances, and then as you kind of go down, there's a lot of categories here that there might only be a handful of instances throughout the data set. Yeah, so each of these data sets are going to have unique properties and biases, coordinate systems, focal lengths, etc. Yeah, and kind of the hope here is that you're going to have a lot more variance in the rotation, the size, the layouts, and the intrinsics, and so on. Basically just shitting on the fact that these other images are small, pointing out that Coco has much larger, kind of making the case for needing a bigger data set for 3D. Again, kind of hitting you with the key stats for this new data set that they're proposing. Suitable for general image-based 3D object detection. Okay. We curate Omni3D, publicly available. Yep, this is the stuff they've already said. Okay, 3D cuboid annotations. Semantically align object categories via manual association. Okay, so they basically they decided which of these 97 categories are the same. Maybe tree is the same. Tree in Kitty is the same as plant in Sun RGBD, and they kind of decide to collapse those into a unified category. But again, you couldn't do this with millions of categories, right? You can only do this with a couple. I think 100 is something that you could do by hand. Not that there is a data set that has 1 million categories. Maybe there is, I don't know. There are a total of more than 3 million. Okay, so this is their train test split. Yep, free of video sequences overlapping in splits. This happens a lot, so sometimes in these data sets you'll have a video, right? And a video might have 30 frames in it. Right. You might have this sequence of a car driving out and then taking a left, and there's 30 frames in that. And you shuffle your whole data set, and then you do your normal train test validation split. But because you shuffled it, and because there's basically maybe, 100 frames of this car moving, there's a bunch of very, very similar images. And if you're not careful, you can end up with very, very similar images, basically from the same video sequence, in the train and the test and the validation split. And what you're effectively doing there is basically testing on your training data and validating on your training data, which is one of the sins of machine learning, right? You want to make sure that the stuff that you're testing and validating your model on is not seen in any shape or form in your training data set to really get an actual measure of how good your machine learning model is generalizing. Okay, here we have the definition of what Omni3D in is and Omni3D out. Okay, so Omni3D indoor is going to be your kind of indoor data sets, ARKit, SunRGBD. Omni3D out is going to be Kitty, which is going to be your kind of autonomous vehicle data sets. Okay, we're actually going to switch the microphone here to a different setting, see how that works, and then we'll compare later on. So this is microphone setting 3, and before this I had it on 1. Okay, distribution of object centers. This is what we were looking at. Yep. Omni3D is a center bias, similar to 2D data sets. Yeah, so because they have some autonomous vehicle data sets, right, they're going to have instances that are as far as 300 meters, right, especially if you have something like Kitty. But if you have a lot of these kind of more indoor data sets, they're all going to be significantly closer objects. Yeah, so, right, urban objects appear mostly on a planar ground. This is kind of the vanishing point bias that you see in these autonomous vehicle data sets. Everything's on the same flat surface, kind of, and cars are always kind of like looking forward in such a way that, like, you know, everything's on this plane, right? They're calling this planar ground. And, right, they do say that the kind of outdoor data set based on AV data has much higher correlation than something like Omni in 3D. Here you have some of the categories. Chair, sofa, laptop, table, cup, shoes, book, window, car, truck, pedestrian. Yeah, so it really just looks like they concatenated the indoor scene categories and the autonomous vehicle categories. Okay. Cool. Okay, I think this is where they're going to start talking about their cube RCNN. To be interesting. Let's see kind of what bag of tricks they use to really get the state of the art on this little benchmark that they created. Yeah, it's just okay. It's just a faster RCNN, end-to-end region-based object detection framework. Okay, so you have the backbone network, which is still a CNN. I think I would have loved to see a vision transformer here, especially coming out of Facebook research. Yep. Takes the image, converts it into a basically high-dimensional feature space. Then you have a separate network known as the basically gives you a crop of this feature space, which represents object candidates. And then you have a 2D box head, which just takes the high dimensional feature space cropped out by the region of interest, and then predicts a category and a more accurate bounding box. And then you can have task specific heads, mask RCNN, which creates not just a bounding box, but a little mask. So I think there's one particular picture with a cowboy that's famous here in the paper. But yeah, so here you have the RPN goes from image, or the CNN encoder, right? The backbone goes from image to this brick of features, and then you have the RPN, which right, region proposal network here, which then crops out parts of that, and then these little crops pieces get put into different heads. You can have a head that determines the category, classification head. You can have that same head bounding box regression, so just kind of more accurate deciding which of those boxes, or like how to trim or improve that box. And mask RCNN has a head that creates the mask, right? So this kind of actual, like, very fine, detailed cropping, if you want to say. I don't know if cropping is the right word, but okay. So basically, they seems here that all they really do is they just use the RCNN that they already have, and then they just introduce a 3D detection head, which predicts a 3D cuboid. Okay, here are the different things that they do. They replace the binary classifier in RPN, which predicts region objectness, with a regressor that predicts IOU-ness. Okay, so in the RPN, which is again the model that kind of crops out. Do they have a picture of this? Okay, here we go. So the backbone gives you the feature map, and then you need to basically crop out different parts of this. And the region proposal network, they're saying that in faster RCNN, it's basically trying to predict objectness, and then they're replacing that with IOU-ness. I think we'll get a definition of those terms. Part B, the next modification they do is they introduce a cube head, which estimates the parameters to define a 3D cuboid. Okay, so cube head. Right, so the same way that you would normally have a mask head, they're just now replacing it with a cube head, which predicts these numbers here, right? U, V, Z, we're going to figure out what these are, but, here we go. The cube head represents a 3D cuboid with 13 parameters, each predicted by a final fully connected layer. So, right, this is the definition of the 3D cuboid. You have the projected 3D center on the image plane. Okay, so U and V is still in pixel space. The object's center in depth in meters. Okay, so they're saying the center of the object in image space, or in the image plane. Then they have how far away that center is in meters, in real. So this is the actual, this Z component here is really where you're getting the actual sense of the depth. This is going to be probably the one that's most sensitive to things like focal length and camera intrinsics. Then you have the log normalized physical box dimension. So, okay, then how big is this box? This one's also going to be one of the more tricky ones, right? Because a car that is far away is going to have really big really big dimensions in the real world in meters, but a toy car in Sun GD that's close, it's going to look very similar to that, but it's going to be very, very tiny. So it's interesting. These are going to be the harder ones, and especially in this data set that you have very big objects very far away, and then you have very small objects very close. P represents a continuous 6D allocentric rotation. So this is the actual rotation of the box. So, right, you could have picked a quaternion. Usually, quaternions have kind of discontinuities, which sometimes makes them difficult to predict directly from a fully connected network, or fully connected head. So sometimes what people do is they'll basically take a rotation matrix, which has more numbers, and you don't need all those numbers, right? Quaternions are kind of perfect in that with just 4 numbers you can represent all rotations, but rotation matrices, you have many more numbers, but some of them are redundant. But you can basically pick kind of a subset of those, and that's what they're referring to here by the allocentric rotation. And then finally, they actually directly predict the 3D uncertainty. I think this is good. I think outputting a uncertainty, you see that in 2D object detection models, where not only do you predict a bounding box, but then you also have a confidence around that. Yeah, so the pre-computed anchors, there's basically a bunch of guesses of the bounding box, or basically this RPN gets a bunch of candidate bounding boxes, and then it kind of filters them based on which ones are the most object-y, right? The objectness, right? So it's basically binary classifying these as object or not. So yeah, so they basically say that, hey, rather than kind of using a binary classifier and saying, is this an object or not an object, we have a ton of things in this scene that aren't labeled, like, for example, the curtains or this picture frame here, right? And we'd want to know, we don't want that to influence that, right? So we're going to come up with a new metric called IOU-ness. Which tries to predict the IOU between a region of interest and its ground truth. Okay, so right, they have obviously the ground truth bounding box, and then they know what the overlap of that anchor is to the ground truth, and then they're ultimately trying to predict that. So they're doing regression with that as the label. Okay, so they're using a binary cross entropy loss here. Okay, and actually they're adding an additional loss here, which they're calling the regression loss from the 2D bounding box. So there's 2 different heads here, and they're weighted. So there's a hyperparameter here which determines how much of the loss is determined by this IOU-ness loss, and how much of it is determined by the 2D bounding box regression, which comes from previous work. Okay, so then we get to the cube head, which we were looking at before. Again, this is really just a pretty logical extension, faster RCNN. In the past, people added for example, a task-specific head to predict a mask, and here all they're doing is they're adding a task-specific head to predict the cuboid. Cube head inputs 7x7 feature maps pulled from the backbone for each predicted region. Okay, so what does pooling mean? So pooling is basically a form of reducing the dimensionality by kind of sampling. So let's say you have this is your kind of feature map, and this is a 4x4 tensor of numbers, right? In this imaginary kind of example here. That's a lot of numbers, and you want to, especially if you're going to put that into a fully connected layer, right? Every neuron in a fully connected layer connects to every neuron in the next layer, and 4x4 16 numbers is going to lead to a lot more weights and biases than 4 numbers, right? 16 times 16 versus 4 times 4, right? Versus 4 times 4. I don't know why we had to calculate that. But you can see how there's kind of an incentive here to reduce the dimensionality of that feature space. So that's kind of what they're doing here. They're saying we're going to take what comes out here out of this region proposal network. It's giving us this little box here. There's, I don't know, maybe this is like 15 by 15, or probably more than that, 100 by 100. And then that's way too many numbers to feed into a fully connected layer. So let's pool it down to a 7x7 feature map. And then that's what will feed into the fully connected cube head. All 3D estimations in the cube head are category specific. Huh. That's interesting. Category specific to me suggests that the 2D head that is outputting the class category, that class category is also getting fed into the cube head. So the cube head is conditioned on the category, but that doesn't seem to be what this image suggests. So, interesting. Okay, the object's 3D center X is determined from the predicted 2D center and the depth. So this is just kind of doing a bunch of camera math and triangles in order to get the 3D center X of the object from these numbers that we were looking at, basically going out from image space. Yeah, this is focal length and principal point. So these are camera intrinsic. So whenever you see camera intrinsics, it's things such as this, focal length and principal point, which are camera model focal point. Right. You have kind of a geometry-based understanding of how cameras work, right? This is sometimes called the pinhole camera model, and different cameras will have different, because of the lens, they'll have different focal points, different focal lengths. Principal point is another, it's not on any of these pictures, but it's another one of these kind of terms. Okay. .3D box dimension. Log normalized with category specific pre-computed means. Yeah, this is honestly kind of lame. You know, it's like they're there's all this extra crap that they're doing. Category specific pre-computed means. So like for each of the 97 categories, they have these basically extra parameters, which are kind of the average width, height, and length of that category, and then they're using that to normalize the width, height, and length when they train this network, and then they multiply it out at the end for inference. But that means that you now have to store this extra crap, right? Which is not great. Okay, then you have a rotation of the object as a rotation matrix. Yeah, rotation matrix is 3 by 3, but they're basically converting that into a 6D parameterization of it. And then this is the final 3D cuboid. Okay, then they have kind of 3D uncertainty in each dimension. Or is it just one number? Confidence, and then join with the classification score S from the 2D box head. Okay. To form a final score. So you want some kind of score that between 0 and 1 that tells you how confident this network is about its prediction. So they're combining the classification score S with this uncertainty that they're predicting in the bounding box, and then combining that here in order to give you a final score. Training consists of 2D losses, 2D box. Okay, cubehead introduces the 3D losses via a chamfer loss. Okay, so they have the 3D bounding box, and from that they get it's 8 points in 3D space, and then they're using what's called a chamfer loss between the ground truth bounding box . Yeah, this is kind of interesting. They say here that it entangles all the 3D variables via the box predictor. What the fuck is this? Okay, so this chamfer loss, right? Because you have the 3D bounding box, and you're comparing the ground truth 3D bounding box, the ground truth 3D, those 8 numbers, the 8 corners of the 3D bounding box. You're comparing the ground truth version of those with the real version of those, right? Your loss is going to be all the variables here that you predicted here that eventually are fed into this are going to be all jarbled up, and it's not going to be possible to kind of separate the effect of one from the other. So what they do is they create I guess 8 separate losses, and then each loss will substitute all but its variables with the ground truth. So basically you kind of put in the ground truth and then only replace them one at a time. And that's how you get the ultimate loss here. Interesting how this is 1, right? So it's not squared. L1 loss, linear. Variable group. Okay, so it's the individual. There's different variable groups here. There's U, V, Z, W, H, L, and then chamfer for the points. Oh, okay. And the reason they do this chamfer loss is because to account for cuboid symmetry. So, like, let's say you have this couch here, right? If your network predicted this bounding box, this 3D bounding box, and it was all perfect except it was rotated by 180 degrees, you wouldn't want to penalize that, right? Because it's actually that 3D bounding box overlaps very well with the actual couch. So they want to allow for the symmetry of the cuboid, which is why they have this chamfer loss. Losses in box have natural advantages over losses which directly compare variables. Okay, so this is the final loss, which is kind of this huge mishmash of crap. We have the region proposal network loss. We have the 2D classification loss, or maybe the 2D head, which is the 2D loss, I suppose. Then we have mu is helpful for both improving and reducing the loss of hard samples during training. So I think mu is the score from up here. Yeah. Mu denotes a learned 3D uncertainty. So then you basically have the uncertainty modulating these terms here, where you have the different 3D losses, the loss for the depth, the loss for the image coordinate, the center of the object in image coordinates, the loss for the normalized width, height, and length, and then this chamfer loss. What is this image saying here? Varying gamma intrinsics, right? So things such as focal length exaggerate scale, depth, ambiguity, right? So is it something that's big and far away, or is it something that's small and close? We should address this by introducing a virtual camera system, which is invariant to intrinsics and transforms the object's depth to a virtual depth, such that the effective image size and focal length are consistent. Yeah, so here they show you how if you're in kind of a world camera frame, the depending on the focal length S, you're going to have a different depth. And they do some camera geometry to basically make it more consistent. Virtual depth. I guess that's what they explain here. Yeah. Yeah, again, I think the problem with this, of course they did, this is kind of an engineering solution where, hey, when the camera's all the same, you can just directly predict the depth in meters. When you have a bunch of different cameras, it's going to be difficult to do that. In order to get good results, we're going to basically create these hyperparameters, effective image height and focal length. But that also means that when you predict and you're doing inference, you're going to have to know what these numbers are for your camera in order to get good meter depth predictions. Okay, let's look at the experiments. How much more do we have left here? So ends about 14, and we're on page 6. Yeah, again, this data set is great for generalization, and that's kind of what they're going to show, how it's great for generalizing, and also anything that's good at generalizing is useful for pre-training. Detectron 2 is Facebook's kind of 2D detection toolkit, which you can find on GitHub. Still pre-training on ImageNet. 128 epochs, batch size of 192. 48 V100s. That's just crazy, right? I think we were looking at these before. V100s are like $10,000. So $48,000 or $480,000 worth of GPUs. That's a really high learning rate, which is interesting. Right, random augmentation of flipping. Okay. Yeah, why not vertical flipping? Well, because car data sets, it doesn't mean anything, you know? It's all these little tricks, right, where you can use data augmentation of horizontal flipping because in this scene, if you flip it left to right, it still makes sense semantically in the real world that you would have the couch on the left and the bed on the right, or the bed on the left and the couch on the right. But if you flip this upside down, it no longer makes any sense, right? You wouldn't have a bed on the ceiling and a couch on the ceiling. So I think, again, you're kind of letting the human knowledge and human bias just creep into the way that these things are implemented and trained. All source code and models will be made publicly available. Living in the future, guys. Okay, so average precision is going to be their kind of score. Yep, then this is their IOU3D. Fast IOU3D. They compute the mean average precision over all 50 categories. At different thresholds. So this is interesting. So in 2D, the AP thresholds for Coco. AP thresholds, computer vision. right, so how much of an overlap do you need for it to be considered a good prediction? So for example, here you can see different thresholds of the IOU. So if you only count IOU of 0.9 for a threshold, it needs to be right on the money, right at the right size in order for it to count. If you have a very loose threshold, you're going to have a much higher score, because even a prediction that's not quite right on the object is going to count. So they say that in 3D, the IOU scores are way worse. So they have much lower thresholds here. They have 0.05 and then 0.5. So even just a tiny amount of overlap between the ground truth and the prediction is going to count. So something to take into account, that this is a way for them to kind of cheese their results, if you will, right? Like they can kind of pick these thresholds such that their results look good. More kind of cheesing here. They get rid of objects with high occlusion and small objects. Okay, let's see what their IOU 3D is. Prior implementations approximate IOU by projecting 3D boxes on a ground plane and multiplying the top view 2D intersection to compare 3D volume. Okay, this is their algorithm here. Represents cuboids as triangular meshes and finds face intersections. Okay, they write this with C++ and CUDA, which means it's like blazingly fast. It's kind of cool. That's some badass software engineering right there, you know, and it's just reduced to one little section of this paper, but that's honestly kind of the coolest part. Obviously, other than the all the hard work into creating this giant data set and re-annotating that and retraining these benchmarks here. Okay, they do some ablation studies. Domain specific, so kind of the two subsets, the indoor Omni3D and then the outdoor Omni3D. One of the ablations is the virtual depth. Kind of shows you how it improves. Okay, so we have here the ablations. IOU thresholds, so average precision at an IOU threshold of 25, average precision at an IOU threshold of 50, average precision for the different depth of the object, right? So something that's within 10 meters, something that's from 10 meters to 35 meters, and then something that's further away than 35 meters. So out of these we see right, if you need 50% overlap in order for it to count as a prediction, you're going to get a very low score. So 25% overlap is really the number that they bring out here. Model does a lot better for near objects, right, less than 10 meters away, than for far objects. And then here is all the different ablations here. So you can see that the best one is 27. So without the disentangled cuboid, pretty much getting the same. without the IOUness score instead of the objectness score, you lose a little bit. For the whatever this is, loss all 3D. Scale augmentation, scale or virtual depth. So actually, that gives you another 5%. Scale augmentation, another 5%, and then uncertainty actually gives you a very large bump, which is interesting to see. They compare to GUPNet and M3D RPN, and then an extension of it, M3D RPN++. And yeah, the results are significantly better here. Almost beating it, all of these across the board here. But again, I mean, these are going to kind of be picked for that. Yeah, this is kind of the coolest part. So it serves as a measure of confidence for the model's 3D prediction, and removing it means that the model would rely on this 2D classification to score cuboids. So there's just like kind of boring shit here. They're just too many acronyms, too many numbers that don't matter because all these models are old, and who the fuck cares about autonomous vehicles at this point, you know? I feel like autonomous vehicles is going more towards an end-to-end kind of approach. I think all robotics is going towards that. And in these kind of end-to-end approaches, having these kind of intermediate perception pipelines where you're trying to get 3D bounding boxes and then use those 3D bounding boxes in a control framework or a control pipeline, I think all of that's going away. I think there still is holdouts, and even in the leading categories such as Tesla, there's still kind of this separation of perception and control. But I think if you look 50 years in the future, you're not going to have that separation. The perception is directly going to, it's going to be end-to-end. You're going to go directly from perception to control. Okay, more comparisons here. Total 3D, some other model. This is more of an indoor. So here they're on. Actually, this is the more interesting here. So Cube RCNN trained on just Sonar GBD versus Omni3D in, which has a couple extra data sets. So these two here are kind of directly showing you the difference in pre-training on a bunch of stuff. I would have loved to see Cube RCNN on Omni3D, just all Omni3D, right? Like, how much does the autonomous vehicle data improve your detection of like pillow or fridge? Maybe that's what this is, and it's really not doing that much. Yeah, we show two use cases of Omni3D, a universal 3D dataset which integrates smaller ones and a pre-training dataset. Training on Omni3D and its domain-specific results in higher performance compared to single dataset training. Okay. The domain-specific subsets tend to perform better on their own domain. Okay, we revisit the task, finally here at the conclusion. We revisit the task of image-based 3D object detection by proposing a large benchmark Omni3D. Simple yet effective model, cube RCNN. There is a pedestrian category, which has ethical consideration. All right. Okay. And then that's basically it. Hypersim, each of the different data sets. Egocentric, allocentric. What virtual depth means. Translate a 3D box purple towards its relative ground truth green. Yeah, just showing you how the IOU of 3D boxes is going to be much lower than the IOU of 2D boxes. That's why they have to lower that IOU threshold. Some qualitative examples here. Let's make it a little bit bigger. We have a house, or this kind of indoor kind of office scenes. We have some nice work here, right? Table's pretty spot on. The chairs are spot on. It even gets this chair in the back here, even though all you see is this top and the legs underneath. Chairs, couches, shoes. Pretty good bounding boxes for these shoes. This is autonomous vehicle data, so get the cars. It's pretty good bounding boxes for the cars. This is kind of a weird one here. You have this human jumping for a frisbee. The bounding box for the human is actually wrong. I wonder what the ground truth one is. So these are Coco images, so these images don't have a ground truth. I think that's why they don't show the ground truth. Cool. So that's going to be it for today. We went through Omni3D, benchmark for 3D object detection. Thanks for listening. This week we will be actually receiving a MetaQuest Pro VR headset, so stay tuned for a unboxing video for that, and we're going to start doing some development on it and see what we can get. But yeah, thank you, and see you guys tomorrow.